Hello everyone, so in this video I'm going to talk about dual nature of matter, which is part of modern physics, and I have categorized previous year's questions as problem type. So if you watch this video till very end, you have the idea what different types of questions can be asked from this chapter. Now let us see for whom this video will be beneficial. So if you have some basic knowledge and your NCERT level concepts are clear, and you have done some formal coaching but still you are struggling with numerical part, so this video is for you. And if you want to use this video effectively, first you have to revise the short notes which you have prepared for this particular chapter. Then while watching the video, if you come across any new information, write down that information. And whenever I discuss an illustration, you have to pause the video, try to solve the question on your own first, and if you're not able to solve, then you can see the solution. So if we talk about weightage, around one question can be asked from this chapter, and usually the questions difficulty is not that high. It is very basic question. And if you look at the syllabus, this is the syllabus which we have to focus. So this is the mind map, and if you look at this mind map, there can be a question from the photon part, and the force exerted by the radiation on a surface, and then the De-Broglie's wavelength, and then photoelectric effect. Right, so now let us start with the problem type. So the very first problem type is the number of photons emitted by a source. So if we have given, say, a point source which is having a power P, then the number of photons which this source is emitting, let us say that number is n. So n is the number of photons emitted per second. It will be power divided by energy of one photon, and energy of one photon will be h nu, or we can say hc by lambda. So this formula you have to remember. Let us see a question based on this concept. A parallel beam of light of wavelength 900 nanometer and intensity 100 watt per meter square is incident on a surface perpendicular to the beam. The number of photons crossing 1 centimeter square area perpendicular to the beam in 1 second. So we have given a surface, and on this surface photons are being incident normally, right? Area is given, so area is given as 1 square centimeter, and watt per square meter is nothing but the intensity, so that is intensity. So intensity is given as 100 watt per square meter. Now if we multiply intensity with the area, we'll get the power. So power will be I times A. So it comes out to be what? It is in meter square and this is in centimeter square. So we can say it will be 100 multiplied with area will be 10 raised power minus 4 meter square, right? So this comes out to be 10 raised power minus 2 watt. Okay, so power will be in watt. And we have to find the number of photons crossing this area. So we know the formula, right? So number of photons will be per second crossing the area will be P lambda by Hc, right? So power is 10 raised power minus 2, lambda is 900 nanometer, which can be written as 9 into 10 raised power minus 7 divided by H, and C, H is 6.626 into 10 raised power minus 34, and C is 3 into 10 raised power 8. So let us simplify this. So this will be 3, and we will get 3 upon 6.626 times 10 raised power minus 9 plus 34 minus 8. Right, so this comes out to be 17, 34 minus 17, so it will be 17 only, right? So we get 3 upon 6.626 into 10 raised power 17. So if you look at this, it will be nearly 0.45. So 0.45 into 10 raised power 17, so which comes out to be 4.5 into 10 raised power 16. So option B is the right answer, right? Now let us see the next problem. So monochromatic light of frequency 6 into 10 raised power 14 Hertz is produced by a laser. The power emitted is 2 into 10 raised power minus 3 watt. How many photons per second on an average are emitted by the source? So again we have to use P upon H nu formula, right, or Hc by lambda. So this power is given We know what is h, we know the frequency. So let us just put the values. So it will be 2 into 10 raised to power minus 3 divided by 6.63 times 10 raised to power minus 34 times 6 into 10 raised to power 14. So which comes out to be 1 upon 6.63 times 3 times 10 raised to power 34 minus 17. So which comes out to be 1 upon nearly 20, right? Times 10 raised to power 17. So it will be 0.05 into 10 raised to power 17. So 5 times 10 raised to power 15. So option 3 is the right answer. Now let us see the next problem type, and it is based on the intensity of radiation. So if we have given a point source which is having a power P, and we want to find the intensity at a distance R from the source. So intensity is defined as power upon 4 pi r square, which is the surface area of a spherical shell which is having a radius r. Now let us see the question based on this formula. Nearly 10% of the power of a 110 watt light bulb is converted to visible radiation. The change in average intensity of the visible radiation at a distance 1 meter from the bulb to a distance 5 meter is A times 10 raised to the minus 2 watt per meter square. So in this question we will have an assumption that the light bulb is behaving like a point source. So we can use this formula P upon 4 pi r square, and the change in the intensity is given as A times 10 raised to the minus 12. So we can say power is what? So the power of the visible radiation will be 10% of 110. So we can first find the power of radiation. So that will be 10% of 110 watt. So which comes out to be 11 watt. So 11 watt is the power. So change in intensity will be power of radiation divided by 4 pi 1 square minus power of radiation divided by 4 pi 5 square. So from this we can say power of radiation upon 4 pi will be common, and we'll get 1 minus 1 by 25. So power of radiation is 11 upon 4, and we can write pi as 22 by 7, and this will be 24 by 25. So let us simplify this. So this will give us 2, and we have 8, so this will give us 3. So it comes out to be 21 by 25. Now if you look at the question here, we have given it, this is equals to A times 10 raised to the minus 2. So it is given as A times 10 raised to the minus 2. So A comes out to be 2100 by 25. So if we simplify this, so this will be 5 and it will be 420. It comes out to be 84. So A is 84. So 84 is the answer. Right, so the next problem type is based on the force applied by the radiation on a surface. So here we're going to consider normal incidence. So if we have a perfectly reflecting surface and the photons are being incident normally, so the force exerted will be 2 times I A by C, where I is the intensity, A is the area of the plate, and C is the speed of light in vacuum. In case of a perfectly absorbing surface, the force will become IA by C, and if we have a partial reflecting, in that case force will be IA by C times 1 plus R, where R is the fraction of the photons which is getting reflected. Now let us see the problems based on these concepts. Average force exerted on a non-reflecting surface. Non-reflecting means perfectly absorbing, right? At normal incidence is 2.4 into 10 raised to power minus 4 Newton. So force is given. If 360 watt per centimeter square, so that is the intensity, is the light energy flux during a span of 1 hour and 30 minutes, and then the area of the surface. So we know that in case of perfectly absorbing, force is IA by C, and what is the intensity? So first we have to convert intensity into SI units. So it will be 360 divided by 10 raised to power minus 4 watt per square meter. So we got intensity, we have given force, C we know, right? And this time duration is of no use in this problem, so they have just given this value to confuse you. So we have to find the area. So force is 2.4 into 10 raised to power minus 4. Speed of light in vacuum is 3 into 10 raised to power 8 divided by the intensity, which is 336 into 10 raised to power 5. So let us simplify this. So this will be 0.2 and this will be 3. So 3 will get cancelled out. So it comes out to be 2 into 10 raised to power minus 5 plus 8 minus 5. So it will be 2 into 10 raised to power minus 2, which is 0.02 square meter. So option 4 is the right answer. Let us see another problem. 50 watt per square meter energy density of sunlight is normally incident on a surface of solar panel. Some part of the incident energy, 25%, is reflected. It means 75% is getting absorbed. And right, so the force exerted on 1 square meter area will be, so here we have normal incidence. So we're going to use this formula IA by C 1 plus R, where R is the fraction of the photon which is getting reflected. So R is nothing but 25 by 100, which is 1 by 4. So let us substitute the values. Intensity is given as 50, area, it's a 1 square meter area, so 1 divided by 3 into 10 raised to power 8 times 1 plus 1 by 4. So this comes out to be 50 by 3 times 10 raised to power minus 8 times 5 by 4, which is 250 by 12 times 10 raised to power minus 8. So which will be close to 20, right? Around 20 into 10 raised to power minus 8 Newton. So option B is the right answer. Now that is the next problem type, and it is based on the De-Broglie's wavelength of a particle. And let us first see the important formula that we have to remember. So De-Broglie's wavelength will be given as h by linear momentum, right, where h is the Planck's constant, and linear momentum can be written as root of 2 mk, where m is the mass of the particle and k is the kinetic energy. And suppose if we have accelerated a particle at rest with a potential difference of v, right, say charged particle, then this k can be written as q times the potential difference. So this can also be written as h upon root of 2 mqv. So these formulas you have to remember. Right, so let us see a question. The De-Broglie's wavelength of proton and alpha particle are lambda and 2 lambda respectively. The ratio of the velocities of proton and alpha particle. So De-Broglie's wavelength is given and we have to find the ratio of velocity. So we know De-Broglie's wavelength is h upon p. P is nothing but linear momentum, so it will be mv. Right, so we can say lambda 2 by lambda 1 will be equals to m1 v1 upon m2 v2, right, because lambda is inversely proportional to mv, and h is same for both the particles. So the ratio of the velocity of proton, so 2 is I'm taking 2 for proton and 1 for alpha particle. So lambda 2 by lambda 1 will be mass of the alpha particle is 4 times mass of proton times velocity is velocity of alpha divided by mass of proton will be m, and the velocity of proton is say vp. So this will get cancelled out, and lambda 2 is given as that is for proton, yeah, so lambda 2 is for proton, which is lambda, and for alpha particle it is 2 lambda. And we have to find v alpha by vp, which comes out to be 1 by 8, right? So option 1 is the right answer. Now let us see the next question. A proton and an electron are associated with same De-Broglie's wavelength. So they have their De-Broglie's wavelength is same, and the ratio of their kinetic energy is, so we know that lambda is h upon root of 2 mk. So De-Broglie's wavelength is inversely proportional to square root of the product of mass and kinetic energy. but they have same De-Broglie wavelength, right? So from this we can say lambda square by h square is equals to 1 by 2 mk, where lambda is constant, h is constant, right? So we can say k times m will be constant. If k times m is constant, so we can say kinetic energy of proton times mass of proton should be equals to kinetic energy of electron times mass of electron. So Kp upon Ke will be mass of electron upon mass of proton. And mass of proton is around 1836 times more than the mass of electron. So this can be written as 1 upon 1836. So option 4 is the right answer. Now let us see the next problem. An electron of mass m and photon having same energy E. The ratio of wavelength of electron to that of photon is. Okay, so if you talk about electron, energy of the electron will be, you can say half mv square, right? And this will be half mv square, where v is the velocity of the electron. Or we can write this as p square by 2m, where p is the linear momentum of the electron. And we know that linear momentum is h by lambda. So we can write this as h square upon 2m lambda square. Let me call this as lambda e. So lambda is the De-Broglie wavelength for electron. And we can, and this e is also equals to h c by lambda of photon, because the energy of photon is given by h nu, right? So now what we have to do, so let us find lambda e. So lambda e will be, from the first equation, it will be h by root of 2me, and lambda of photon is hc by e. Now we have to find the ratio of these two wavelengths. So lambda e by lambda photon will be what? It will be h by root 2me times e by hc. So h will get cancelled out, and this comes out to be 1 by c times root of e by 2m. So option 2 is the right answer. Okay. Let's see the next problem. A nucleus of mass capital M at rest splits into two parts having masses m prime by 3 and 2m prime by 3, where m prime is less than m. It means the sum of the masses of the product is less than the mass capital M. It means some of the energy, some of the mass has been converted into the energy. So the ratio of De-Broglie's wavelength of two parts will be, okay, right? So we have so capital M is splits up into two parts. So let us say this mass is m prime by 3, and this is another mass which is 2m prime by 3. So since it's an isolated system, so the linear momentum will be conserved. So if m prime by 3 is going in the left direction, then 2m prime should go in the right direction. If this is the linear momentum of left mass and p2 is the linear momentum of the right mass, then we can say p1 and p2, the vector addition of these two momenta should be 0. Why? Because we have given capital M was at rest initially. So initial momentum of the system was 0, so the final momentum has to be 0. So we can say their magnitude should be equal, right? So if the linear momentum has the same magnitude for both the particles, then we can say the De-Broglie's wavelength is also same. So option C should be the answer of this question. Let us see the next problem. A proton and an alpha particle are accelerated from rest by 2 volt and 4 volt potentials respectively. The ratio of the their De-Broglie's wavelength. So here we have to use the relation between De-Broglie's wavelength and the potential that we have used to accelerate the charged particle. So we know that De-Broglie's wavelength is h upon root 2mqv. So if you look at this, lambda is inversely proportional to square root of mqv, right? So basically we have to check for this for the ratio of 1 upon root mqv. So for proton and for alpha particle. So 1 upon root. What is the mass of proton? I'm taking it as m, and the charge on the proton is E, and the voltage that is given is 2 volt. Similarly for alpha particle, this ratio will be so 1 upon root. Mass of the alpha particle is 4 times the mass of proton, and the charge is 2 times the charge of proton, and the potential is 4 volts. So if it's this Me2 will get cancelled out, so it will be 1 ratio 1 by 4. So 4 ratio 1 should be the answer. So option 1 is the right answer. Let us see another question. The De-Broglie's wavelength of a molecule in a gas at room temperature 300 Kelvin is lambda 1. If the temperature of the gas is increased to 600 Kelvin, then the De-Broglie's wavelength of the same gas molecule becomes. So first of all, we should know what is the relation between the temperature and the kinetic energy of the particle, right? So here kinetic energy is proportional to the temperature. And we know that De-Broglie's wavelength can also be written as 1 upon root, sorry, h upon root 2 m k, right? So if mass is constant, then lambda will be inversely proportional to square root of the kinetic energy. And kinetic energy is proportional to the temperature. So we can say De-Broglie's wavelength is inversely proportional to square root of the temperature. So from this we can say lambda 2 by lambda 1 should be equals to root of T1 by T2 by using this proportionality. And lambda 2 we have to calculate. So lambda 2 is lambda 1 times root of T1 by T2, and T1 is 300 and T2 is 600. So it comes out to be lambda 1 by root 2. So option 1 is the right answer. Okay. Now let us see the next problem type, and it is based on the threshold frequency and threshold wavelength that you study in photoelectric effect. So that is the first question. The threshold frequency of metal with work function 6.63 electron volt. So we know that work function is given as h times nu naught, where nu naught is the threshold frequency. Now from this phi is given as 6.63 electron volt, and 1 electron volt is 1.6 into 10 raised per minus 19 joules. Now divide this with the Planck's constant, so 6.63 into 10 raised per minus 34. So that will give us the threshold frequency. So 6.63 will get cancelled out, so we'll get 1.6 into 10 raised to power 15, or you can say 16. Alright, so so we have to find answer in term of 10 of the order of 10 raised to power 15 only, right? Yeah, so option 4 is the right answer. Let's see the next question. The work function of a substance is 3 electron volt. So work function is phi, which is 3 electron volt. The longest wavelength of light that can cause photoelectric emission from the substance is approximately. So we have to find the longest wavelength, and longest wavelength which can carry out photoelectric emission is threshold wavelength. So phi can be written as hc by lambda naught, where lambda naught is the threshold wavelength. So 3 into 3 electron volt. And if you want to find wavelength in nanometer, then hc by lambda can be written as 1240 divided by lambda in nanometer. Okay, we can use this approximation. So this comes out to be 1240 upon lambda in nanometer, and this this entire thing should be in electron volt. So this is in electron volt, and it is given as 3 electron volt. So we can say lambda in nanometer will be 1240 by 3, so which is nearly equals to 413.3, something like that, 413. So option 2 is the right answer. So you should remember this, right? This formula is required. Now let's do the next problem time, and it is based on Einstein's photoelectric equation. And what is the equation? So if we have given energy of the photon, which is h nu, it should be equals to sum of the work function and the maximum kinetic energy attained by the photoelectron. And this k max is nothing but E times the stopping potential. Right, let us see. So the first question is, When a metal surface is illuminated by light of wavelength lambda, the stopping potential is 8 volt. So it means K1 is 8 electron volt. And when the same surface is illuminated by light of wavelength 3 lambda, the stopping potential is 2 volts. So K2 is 2 electron volt. So when we are not changing the target material or metal, then the work function will remain same. So let us apply Einstein's photoelectric equation 2 times. So we can say Hc by lambda is equals to phi plus 8 electron volt, and Hc by 3 lambda is equals to phi plus 2 electron volt, and we have to find the threshold wavelength. So let us eliminate Hc by lambda from these two equations, and we can find phi value. So let us first find phi. So if we divide both equations, so we'll get 3 equals to phi plus 8 upon phi plus 2. So from this 3 phi is equals to phi plus 8, and phi comes out to be 3 phi plus 6, sorry, right? So this comes out to be 2 phi is equals to 2 and phi is equals to 1 electron volt. So we got work function, and if I substitute work function in one of the equation, let us substitute work function in the first equation, then Hc by lambda comes out to be 9 electron volt, right? Or you can say Hc is 9 lambda electron volt. So let us substitute Hc as 9 lambda electron volt in the first equation. So that will be 9 lambda by lambda equals to, and work function can be written as Hc by lambda naught plus 8. So this will be 1, and Hc is 9 lambda. So lambda naught comes out to be 1 by 9. Sorry, lambda naught is 9 times lambda. So option 3 is the right answer. Let's see the next question. In photoelectric experiment, energy of 2.48 electron volt irradiates a photosensitive material. So that is the energy of the incident photon. So that is h nu. The stopping potential was measured to be 0.5. So we can say K max is 0.5 electron volt. We have to find the work function. So we can say h nu is work function plus K max, and h nu is given as 2.48, and if we subtract K max from this, so minus 0.5, we will get the work function in electron volt, and which comes out to be 1.98 electron volt. So option 3 is the right answer. So can you see most of the questions are direct application of the formula. So that's why this chapter is must. When UV light of wavelength 300 nanometer is incident on a metal surface having work function 2.13 electron volt, electron emission takes place. The stopping potential, right? So we have given wavelength in nanometer, so we can use and we have given Hc can be written as 1240 electron volt nanometer. So we can say Hc by lambda is 1240 electron volt times nanometer divided by lambda. Lambda is 300 nanometer, right? So this comes out to be 4.13, right? So 4.13 electron volt. So that is the energy of incident photon, and work function is given as 2.13 electron volt, and we have to find the stopping potential. So K max is 4.13 minus 2.13, which comes out to be 2 electron volt, and K max is nothing but E times V naught. So V naught comes out to be 2 volts, right? So option 3 is the right answer. Let us see next question. Yes, UV light of 4.13 electron volt is incident on a photosensitive material surface having work function 3.13. The maximum kinetic energy of the ejected photoelectron, so K max is equals to 4.13 minus 3.13, so that comes out to be 1 electron volt. So option 3 is the right answer. Let us see one more question. The electric field at the point associated with the light wave is given by E equals to 200 sine 6 into 10 raised to power 15 t plus sine 9 into 10 raised to power 15 t volt per meter, where H is 4.14 into 10 raised to power minus 15 electron volt second. If this light falls on a metal surface having a work function 2.5 electron volt, the maximum kinetic energy of the photoelectron. So if you look at the formula, or if you look at the equation, Einstein's photoelectric equation, H nu is phi plus K max. So we can clearly see that if we increase the energy of the incident photon, we are able to increase the maximum kinetic energy acquired by the photoelectron. Now in this electromagnetic radiation, in this electric field, there are two different types of photons. So one photon has an angular frequency of 6 into 10 raised to power 15, while the other photon is having an angular frequency of 9 into 10 raised to power 15. So if we want to maximize the K max, we have to use photons which is having more frequency, right? So we're going to use 9 into 10 raised to power 15 instead of 6 into 10 raised to power 15. So the frequency that that we have to use is omega by 2 pi, which will be 9 into 10 raised to power 15 divided by 2 pi. So that we have to use. So if we use that, the energy of the incident photon will be h times f, which will be 9 into 10 raised to power 15 divided by 2 pi, and h is given as 4.14 into 10 raised to power minus 15 electron volt second. So multiply this with 4.14 into 10 raised to power minus 15. So this will give us the energy of the photon in electron volt, right? So this will get cancelled out. So we have 2.07 times 9 divided by pi electron volt. Now we can apply Einstein's photoelectric equation. So it will be 18.63 by 3.14 minus work function, that is 2.5, and that will be K max, right? So if you look at this, it comes out to be nearly 6. 6 minus 2.5 will be 3.5. So the option D, so the answer comes out to be 3.42 electron volt. So that should be the answer, right? 3.42. Option D is the right answer. Right, so let us see this question. A metal surface is illuminated by a radiation of wavelength 4500 angstrom. The ejected photoelectron enters a constant magnetic field of 2 millitesla, making an angle of 90 degree with the magnetic field. If it starts revolving in a circular path of radius 2 millimeter, the work function of the metal is approximately, okay, so let us see what we have given here. So there is a metal, and we are in some photons are being incident, and the electron, suppose the electron is ejected in this particular direction, right? So that is an electron, and there is a magnetic field which is perpendicular to the ejected velocity of the ejected electron. Let us say the magnetic field is into the plane. Velocity is in the upper direction, so we can say it will experience a magnetic force in the right direction, and due to that it will start moving in a circular path, and the radius of this circular path is given as 2 millimeter. And if you remember, radius is nothing but mv upon EB, right? And this mv is nothing but the linear momentum, so that is, or it can be written as root of 2 mk, right? And the kinetic energy, and we have to find the work function. So kinetic energy by photoelectric equation can be given as the energy of the incident photon minus work function. Okay, so first step would be finding the kinetic energy. So from this equation, let us find the kinetic energy. So if we square this, so we'll get r square e square b square divided by 2m. So that will be the kinetic energy. Let us put the values. So 4 into 10 raised to power minus 6, that is the square of the radius, times E square. So it will be E times 1.6 into 10 raised to power minus 19. And then B square, B is given as 2 millitesla. So that will be 4 into 10 raised to power minus 6 divided by 2. And the mass of the electron is 9.11 into 10 raised to power minus 31. So this is the kinetic energy in joules. Now if I divide this with 1.6 into 10 raised to power minus 19, we'll get the kinetic energy in electron volt. So let us divide this with electron volt, 1.6 into 10 raised to power minus 19. So this E will cancel out with this E. So that will be in electron volt. So let us simplify this. So we have, so this will be 2. So we have 8 into 1.6 divided by 9.11 into 10 raised to power minus 6 minus 19 minus 6 plus 31. So that comes out to be 31. Yeah, so this will get cancelled out, and so that much electron volt, right? So it will be 48, 12, 12.8 upon 9.11. So that will be nearly equals to 1.33 or something, 1.35, right? So 1.35 electron volt is the kinetic energy, maximum kinetic energy, and we have to find the work function. So work function will be energy of the incident photon. So here it is 4500 angstrom. So so the energy of the photon will be given as 12400 divided by 4500. So this will be around 2.90. So then we have 34, around 7, right? So 2.7 electron volts. So it will be 1.35. Sorry, work function is not 2.7. No? This is the energy of the incident photon, h nu. K max is this. So work function will be 2.7 minus 1.35. So it will be nearly 1.35. So option A is the right answer. So the last problem type is based on the theoretical and the graphical questions from photoelectric effect. Now let us see some of the questions. Photoelectric effect, the maximum kinetic energy of photoelectron is plotted against the frequency. So this is frequency and this is the kinetic energy of the incident photon. So this is the frequency of the incident photon. The slope of the graph gives. So if I write down photoelectric equation, I can say h times nu will be equals to 5 plus k max. Or we can write kinetic energy is h nu minus 5. If you look at this equation, it looks like an equation of a straight line. So y equals to mx plus c, where h is the slope, right? So that is the slope, and minus 5 is the y-intercept. So the slope will be Planck's constant. So option 4 is the answer of this question. Let us see next question. Which of the following, which figure shows the correct variation of the applied potential with the photoelectric current I at two different intensities I1 and I2, where I1 is less than I2 of same wavelength? So wavelength is same, so or you can say the frequency of the incident photon is same, but we are altering the intensity. And what do we mean by intensity? If we increase the number of photons incident, then we are increasing the intensity. So as we increase the intensity, then the saturation current increases, right? So and the stopping potential depends only on the frequency, right? We are not altering the frequency, so both the if we alter the intensity, the stopping potential will remain same. So option 2 is the right answer, because in case of I2 we are getting more saturation current, right, instead of I1. So option 2 is the right answer. Let us see the next question. In photoelectric effect experiment, a light of frequency 1.5 times the threshold frequency. So frequency is 1.5 times nu naught, and is made to fall on the surface of the photosensitive material. Now if the frequency is halved, so now if V becomes V by 2 or nu becomes nu by 2, and the intensity is doubled, the number of photoelectrons emitted will be, right? So as we increase the intensity, the number of photon instant will also get doubled, but the new frequency is less than the threshold frequency. So let me call this, so nu 2 is less than nu naught. So there will be no photoelectric emission, because to carry out photoelectric emission, frequency has to be greater than or equals to the threshold frequency. So option 3 is the right answer. Let us see next question. Given below are two statements. So assertion A is given as number of photons increases with increase in the frequency of light. So as we increase the frequency, it does not alter the number of photons. Number of photon depends upon the intensity. So assertion is wrong. Reason is given as maximum kinetic energy of emitted electrons increases with the frequency of the incident radiation. Yes, as we increase the frequency, the maximum kinetic energy increases. So A is incorrect and B is R is correct. So option 3 is the right answer. Let us see next question. So here we have given a graph. Statement 1, figure shows the variation of the stopping potential with the frequency nu for the two photosensitive material M1 and M2. Okay, first let me write down the equation. H times nu is equals to work function plus E times V naught, where V naught is the stopping potential and nu is the frequency. So we can write V naught as H nu H by E nu minus phi by E, right? So slope gives value of H by E, where H is the Planck's constant, E is the charge of electron. So if you look at this equation, it is of the form of y equals to mx plus c. So H by E is the slope, right? If this angle is theta, this is also theta, because it slope depends upon the constant quantities, Planck's constant and the charge on the electron. So statement 1 is fine, right? That is correct. Now look at the statement 2. M2 will emit photoelectrons of greater kinetic energy for incident radiation having same frequency. If the frequency is same, kinetic energy should also be same, right? If we have the same material, but here we have different material, so we can say kinetic energy will be h nu minus phi. So we have to check in which case the work function is more, and if you look at the graph, we can say the y-intercept, magnitude of the y-intercept in case of M2 is more. If phi is more, kinetic energy will be less. So we can say in case of M1, the kinetic energy will be more. So M2 will emit photon. So statement 2 is incorrect. So statement 1 is correct, statement 2 is incorrect. So option 4 is the right answer. Now let us see another question. Which of the following statement is not true about the stopping potential? So it is 1 by E times the maximum kinetic energy of the electron emitted. So it is saying 1 by E times K max is stopping potential. Yes, that is fine. But we have to find the statement which is not true. So option 1 is incorrect. It increases with increase in the intensity of the incident photon, incident light. Right, so when we increase the intensity, we are not changing the energy. We are not changing the energy of the photon. We are only increasing the number of photons. So statement 2 is incorrect. So that should be the answer, right? And it depends on the nature of the emitter material. So that is also true. So this is incorrect. It depends upon the frequency of the incident light, stopping potential, right? So it depends on, yes, it depends upon the frequency. So again, this is true. So it is not the answer. So option 2 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description.
And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.